Okay, so today we go with the JFET again. Okay, JFET setup junction field effect transistor. Okay, they will be FET that operates with a reverse bias PN junction to control the current in the channel. Okay, so basically you get two different types. One will be a N channel, and the other one will be P channel. Okay, so N channel, the arrow you can see, they will be pointing in. Okay, P channel, arrow pointing out. And the first thing you can see, you get the drain, you get the gate, and you get the source. Okay, and basically they can display for you the physical for N channel and also P channel. And they get the VDD here. That will be provide for the drain to the source, okay, voltage, and supply the current from the drain to the source. VGE, okay, set the reverse bias voltage between the gate and the source. JFET always operate with the gate source PN junction in a reverse bias. Okay, so this one we already showing you. Basically, for the first display here, you get a VGS will be more negative. Okay, that is the current ID will be less. And when VGS less negative voltage, the current ID will be increased. Okay, so basically this is the channel from the drain to the source. Okay, if the channel wider, more electron moving, the current will be more. Okay.
Mr. Fan, I have a question about this.
Yeah, go ahead.
This slide. It's tough to me to understand a little bit the pictorial representation of the voltage on the gates. The meter, the red part showed the, let's say, the needle more to the positive side, but you said that when it is more negative, we're going to get less current between the source and the drain.
Okay, you can see that will be increase the negative, right? Increase the negative voltage.
Yes, but let's compare that part. That when you compare that part, the red part between A and B, looks like the message is opposite.
So you think this will be positive. Is it right?
I see that the negative is under the red part and the positive is in the gray area.
Yeah, this is a negative, right?
Okay.
When you let negative, that will be telling you the channel wider and the current ID will be more. On this one here, you get more negative. So that's why the channel will be narrow. So let the current flow. So they tell you the current ID will be less. That only thing they want to show you for relation between the VGS and the current ID.
Okay, okay.
More negative voltage than the less current ID. Okay, that is what happened here. Now you can see on that one, they can get more or less than VGS, then the current will be more. Now you can see the channel will be much wider.
Okay, got it. Thank you.
So that's how the current flowing. Okay, and then you can see this is the JFET in here. Right here will be the gate, and this will be the source. And the gate to the source, that's what we call a VGS. Okay, VGS. And also, this is the VD right here, S right here. So the voltage across that part right here, we call a VDS. Okay, now the JFET will be working, will be like the display here. The first thing, this area here, they call an ohmic region. Okay, ohmic area. That means they can be working like the resistance. And now from the VP we call a pin off voltage. Start of the VP, then the current will be constant. Okay, cannot be changed, and they equal IDSS. So what is the IDSS? What is it?
It's the saturation current with a VGS equals 0.
Exactly. That is the maximum current with VGS equal 0. Okay. Normally you're working on the JFET. They given you the IDSS for each JFET. Okay. And when up to the point, okay, the VDS up to the point there will be a breakdown area. Okay. So we not deal with this thing here. That will be burning the cat. So the JFET will be this area, okay? They will be a constant current, okay? And that current equal IDSS. They start from VP up to the breakdown, okay? Now, the maximum drain current of the effect occurs when the gate to the source voltage is 0. That's what they're talking about, IDSS, okay? Make sure you memorize that. IDSS is the maximum current with the VGS equal 0. The drain current is almost constant in the region between VP and VDS maximum before the breakdown. If the drain voltage is too large, JFET will be breakdown. JFET acts like the current source when it's operating along the almost horizontal part of the drain curve between minimum VP and the maximum of VDS. The minimum voltage of VP they call a pin off voltage. Okay. The maximum voltage VDS maximum is called a breakdown voltage. So basically the constant current starts from VP up to the breakdown. Between the pin off and the breakdown, JFET act like current source with the value IDSS. IDSS stands for the current from drain to source with shorted gate. That means VGS equals 0. And also They can be an ohmic region, almost vertical part of the drain curve called ohmic region. That's equivalent to saturation region in the bipolar transistor. Okay, cutoff voltage. The value of VGS that make ID approximate zero. They call a cutoff voltage, VGS off. Remember, at VGS off, ID equal zero. JFET must be operate between VGS equal zero and VGS off. Comparison upping up and the cutoff. VP is the value of VDS at which the drain current become constant and you always measure at VGS equal zero. VGS of and VP always equal in magnitude, but they both opposite in size. Okay, so VP and VGS of will be equal all the time, but they will be opposite. Okay, VGS of negative, VP will be positive. And in the data sheet, normally they given you only one, not both. They can given you either VGS of or VP. That is a very summarize what you have to memorize. Okay, and now if you're looking on this thing here, okay, you can see this is a stand for VGS. VGS equal minus 4 volt, minus 3, minus 2, minus 1, and 0. So when VGS equal 0, the current will be equal IDSS. If you get a certain point, any point, okay, I can say you get a point right here. What the VGS equal?
-2.
If you get a point right here, what VGS?
VGS is
-2.
Minus 2 volt. You see that? At this point right here, you can get a minus 2 volt. And if you go to the left, then you can identify what the ID here, okay? And if you going down, you can get a VDS, okay? So basically, this is the VGS will be controlled, okay? So the JFET, they said the JFET will be a voltage controller. That means you change the VGS, that will be given to you a different value for the current ID and also the voltage VDS. For the bipolar transistor, NPN, that will be a current controller device. The thing is, in the bipolar, you can get IC equal beta IB. When you change IB, you will be change the current IC. So they will be controlled by the current. Okay, however, for the JFET, you change the VDS, you will be changing the current ID and also the VDS. So that will be called voltage controller device. Okay, so make sure if you get any question, anything, just bring it up, okay? Okay, so basically, now they just showing you VGS equal VGS off. Okay, and that will be telling you the current ID will be 0. And now if you're looking in the channel here, okay, no more. Electron cannot moving from the drain to the source. So that's why 0. And make sure you have to understand at the cutoff voltage, then ID equal 0. And VGS will be equal VGS off. This is just given to you the P channel. Basic operation. P channel is the same as the N channel, except that P channel requires negative voltage on VDD and also positive voltage on VGG, okay? So that's completely opposite to the N channel, okay? And also, now if you get an N channel, D here, F here, and that will be G, okay? So VDF, that means here, VDF, basically VD minus VF. And this is a positive, negative, the voltage here, VGF. And VGS will be VG minus VF. That's a basic thing. You must know that. Okay? This is an example. And I try to make sure can you follow this example here. For the JFET circuit show, they given to you VGS off minus 4 volt. And the IDSS equal 12 milliamp. The question is, they want to know what the voltage VDD minimum, okay, to put the device in constant current area. And you understand it, a constant current area. They will be stuck right here. What the voltage here? VP. That will be ID. And the maximum ID at F. And that will be a VDE. DF. Okay. So now they want it working in this area. That means in this one right here. And they want to know what the voltage VDD supposed to. So you can get a D right here, F right here. Okay. So VDD will be supposed to be equal voltage drop across this guy. Okay. So I know VDD supposed to be equal ID times RD. And also you need the voltage here. Let VDS. So in order to solving the problem, you need to know what the ID times RD. ID, they supposed to be ID at S. So you can get the ID at S times RD. Okay, 5600. So on this one here, you can do the calculation. Okay, you can take a 12 milliamp times 0.56. So that's why you can get the VRD, voltage across RD. And now you need to get the VDS. Okay, VDS, you can see right here. Okay, you get the VGS off equal minus 4 volt. That will be telling you VP equal 4 volt. We already said VP VGS off must be opposite. Okay, same value. So that's why they say minimum they asking for VDS must be equal VP and VP equal 4 volt. So that's why you calculate the VRD, then you adding to 4 volt of the VDS, given to you the voltage of the power supply equal 10.72 volt. Okay, you get any question on
Mr. Pham, raise your screen just a little bit. You can't see the bottom. Yeah, right there, right there.
the thing is we have to looking into what they want. Okay, I said again, for the circuitry, they want to know minimum voltage of the VDD in order to make sure the FET will be working in the constant current region. So the voltage VDD will be combined between the voltage drop across RD and the voltage go from D to S. Okay, so in this area, we know the current will be IDSS. So that's why you can calculate the voltage drop across the 560 ohm resistor. Then you adding to the voltage VDS. Minimum for VDS to be in constant region. That means they must be equal VP. And you know VGS off, then you know VP. Okay? That is the whole thing for this example.
And Mr. Pham, also too, so basically we want to operate between the VP and the VDS.
Maximum.
Okay, so then we would have to be operating between, are you saying 4 volts and 10.7? VP is 4 volts.
Okay, VP 4 volt.
So my question is, are we supposed to be operating between VP?
That's not that mean. The key point in here, they want to know VDD, power supply. They want the voltage power supply in order to start for the JFET working in the constant region. Right now, they're not giving you VDD, but they're asking for what is the minimum on that voltage. So you understand VDD will be support for this voltage here and the voltage here, right?
Right.
Okay, so now when they working in the constant here, region here, so you can calculate the voltage drop across the RD. Take the 12 milliamp time resistor, you get the voltage of VRD. Then you need to know what the VDS supposed to be. And if you're looking on the graph right here, start working on the constant region. VDS must be equal VP. And you already know they given you VGS off. Then you know the VP. VGS off minus 4. And VP will be plus 4. Then you adding those two voltage. That given you the voltage for the VDD. That is the whole example. Okay, now the next one they given to you. Okay, JFET transfer characteristic curve for N channel. Okay, you get a point right at this point right here. IDSS. At this point, what VGS equal?
0.
0. You're going down, right? VGS equal 0. And also you get another point, they call a VGS off. At this point, VGS off, we already know ID equals 0. So they draw the curve, okay? So that's what they call a curve, transfer curve, okay? They already explained to you here. ID 0, VGS off equal VGS off, IDR equal IDSS, IDSS, then VGS equal 0. Now, in a little more detail here, they display on the this side here what the VGS equal, okay? And this is the curve, transfer curve. And basically, this is the curve for this equation, ID, okay? ID equal IDSS times 1 minus VGS over VGS off square, okay? If you want to calculate the current ID, then you're using this formula, okay? And this formula equation, they will be not linear, okay? So on this line here, okay, you can get a point here, you go to the right, you get VGS equal minus 1, okay? And also you can get the current ID. Any point in here, they given you the current ID and the VGS, okay? So,
Mr. Pham,
yeah,
the blue curve, you call it a transfer curve, right?
yeah, that's a transfer, you know, that is basically, that's just a curve for this equation here,
Okay, got it. Thank you.
okay? But not normal.
Yeah, got it.
Okay, now, the partial data sheet give a JFET indicate IDSS equal 9 milliamp and VGS off equal minus 8 volt. They using this value, they want to know the drain current ID. So the first thing, A, VGS 0, what ID equal? B, VGS equal minus 1, what ID equal? So forth, okay? So the first one, A, VGS is 0, what ID equal?
IDSS.
Exactly. You must be saying right away, IDSS. So that's why the answer right here. Okay. A, VGS 0, ID equal IDSS, 9 milliamp. And when VGS equal minus 1 volt, okay, then you have to using the equation. I just gave it to you here. ID equal IDSS times 1 minus VGS over VGS off square. So 9 milliamp times 1 minus 1 volt minus 8 volt square, and you get 6.89 milliamp. Okay, and the same way to do calculation for minus 4 volt. So basically, you want to calculate the ID. You must be using the formula IDSS time 1 minus
Very nice.
over VGS of square.
You know,
Any question on
we
this
can straighten you
calculation?
out because you're a captain. Ooh.
Joseph, can you mute?
Can you follow this calculation? The thing is, we just go by very, very basic thing. Technician must know. Okay, let's see what else here. Okay, the forward trend conductance. That transfer conductance. That means the line here. Okay. GM is the chain in the drain current for a given chain in a VGS. Okay, so GM equal delta ID divide to delta VGS. You can see right here. They have to get delta ID. That means you get a one value here, one value here. That delta ID. Okay, and also delta VGS. That means between these 2 points, you can get a delta VGS, and they can get a definition. GM, check those different divided delta. Okay, delta ID over delta VGS, but we don't care about that thing. Okay, that's just a basic definition. In order to calculate the GM, then they equal GM 0 times 1 minus VGS over VGS off. Normally, they given you GM 0. By definition, GM 0, okay, that is the value of GM with VGS equal 0. Okay, must be remember that. What is GM 0? GM 0 is the value of GM at VGS equal 0. Normally, they given you GM 0, so you can calculate the GM. However, if they not given to you, you still can calculate the GM 0 equal 2 times IDSS divide absolute value of VGS off. The thing is GM is 0 is not negative. That's it. Let's see.
Hey, Mr. Pham?
Yeah.
I think for people who aren't familiar with transfer curves, transfer curves usually refer to the ratio of an output value to an input value. And so a transconductance curve refers, and since conductance is current divided by voltage, the transconductance curve is output current divided by input voltage, right?
That's right. You can get the relation, okay, ratio between the delta. That means you have to get 2 points.
Yeah, it's a slope. It's a slope, yeah.
And you get delta I. And 1 point here, 1 point here, you're going down. You get delta VGS. Okay, so that's a definition. Okay. And now this example, they give us the JFET IDSS 3 milliamp VGS of minus 6 YM0 equals 5,000 microsiemens. Okay, using this value, they want to know what is the GM for VGS equals minus 4 volt. So if you substitute the value, Simon, okay, value GM0, 5,000 microsiemens, okay, then you need to change to Siemens. Then 1 minus VGS, oh, they already given to you, okay? That's why you can calculate the current ID using the same IDSS times 1 minus VGS over VGS of square, okay? And if you want to calculate the I in for the JFET, they will be take a absolute value of VGS divided to IGSS if they give it to you. Now, today we start with what we call a JFET for DC buyer. Same thing.
Mr. Pham, can you back up one slide? I think there's a typo on the previous slide.
The typo.
Yeah, if you go back one slide, I think there's, so, yeah, where it says YM0 should be GM0, right?
GM0 here, right?
Yeah. But up here, in the red part, it says YM0 equals 5,000. That should be GM0.
Yeah, GM0.
Okay.
Thank you. Same thing like the bipolar NP transistor. They need the DC power supply to make the transistor working. They fed the same thing. Okay? Many techniques can be used to bias JFET. In one case, gate source junction is reverse bias. Most common bias technique, first one they can call a gate bias, or they will be a fixed bias, cell bias, and voltage divider bias, and current source bias. But they not much using current source. They can using the gate, or fixed bias, the cell bias, or voltage divider. Now, if you're looking on the here, you can see this what they call a fixed bias. How come they call a fixed bias? The reason is you can get a negative VGG right here. That's a fixed bias. If you're looking at the gate, you get a minus VGG here, okay? Then they will be a fixed bias. We start with a fixed bias first. Normally, you can say, I given you example.
Ma'am, can I just ask a real basic question?
Yeah,
And we're on JFETs now. Is this similar to bipolar, the exception being that we're dealing with a different type transistor?
that's a different type.
Right, I understand. But that's what I'm saying. So bipolar and JFET is the same when it comes to these. I mean, the techniques that you would use for the biasing is similar.
They the same mean they must be get the same DC to make it the fat working.
Okay, thank you.
Okay, but the way different. The first way will be a cell bias. Okay, now if I given you example, when you're looking at the gate in here, you get a minus VGG, 2 volt, for example. And resistor here, I can given you 1 mega ohm. Okay, and this will be the gate. That will be the source, and that will be the drain. Okay, now when you get the VGG minus 2 volt, the question is what VG equal? What VG equal?
-2 because the junction is reverse biased.
You say minus 2, that's correct. Okay, however, I can tell you, how come they equal minus 2?
0 gate current.
Okay,
Because the resistor is 1 mega ohm.
yeah. I given you that example here. What we out?
10 volts.
We out equal 10 volt. That's the correct answer. However, you have to tell me why they equal 10.
There's no current, so there's no voltage drop across the resistor.
Exactly. Okay, the reason they open circuitry, the current flowing here. I equal 0.
Mr. Pham, mute the mic, somebody's radio going.
And it's still.
Sorry, I had my TV on.
Okay, so basically open circuitry I equal 0. So the voltage across I here will be nothing, not drop anything. So 10 volt on this side, they will be 10 volt on this side. Okay, now.
Hey, Mr. Pham, just real quick, based on what you just explained, when you get a situation like this, it's basically like the resistor's not there and you're measuring directly across the voltage source. Is that correct?
Exactly, if not resistor here.
Okay, thank you. Thank you.
Now, in here, VGG minus 2 volt, and I say VG equal minus 2 volt. The reason is the current flowing here, I will be equal 0. They suppose resistance is too big, so no current can be flowing through. So that's why VG the same VGG. But they said, how come we don't need that RG? You see that? They still VG equal VGG. Okay? They still okay. But they're not working that way. I explain to you why. Basically, when you're converting, okay, this circuitry to the AC circuitry, okay, for the AC circuitry, on off the voltage, DC must be rounded, okay? So now, if you don't have a resistor here, then gate will be routed, okay? The thing is minus 2 volt will be routed. That will be telling you the sideway, when they go up to the gate in here, they will be go to the route. You don't have any more signal. So that's why they require that resistor here. When you route the VGG here, sideways still go into the gate. That's what I try to explain to you. Okay. No AC signal if you don't have a resistor here. But the thing is, they will be AC route. Okay. So now we will deal with the gate bias, okay, or fixed bias. Try to see how do we calculate it. Okay, let's see. Okay, so basically, the other one they just show you, cell bias. Okay, cell bias, that means you don't have any voltage here. You can see that you don't have a negative voltage here. And in order to do working with the cell bias will be more work to be done. Okay. One of the most common way to bias JFET is cell bias. Only a single power supply yield. That means they're using only one VDD. The drain supply voltage VDD. Okay. So basically they can telling you JFET will be question will be on device or off device. What that mean for on device?
So like a switch?
Now,
The JFET is, if it's on, it's working. If it's off, it's not working.
now,
No? Okay.
so now what that mean for on device? On device in here, I can tell you, they don't need the voltage for the gate, and they still working. That on device. Off device means they must get the power supply, like NPN, PNP, off device. Without the voltage at the base, transistor not working. However, JFET without the power at the gate, they still working. So that's what they call on device. And another one will be voltage divider bias. Okay, so voltage divider, we already get through it in a NPN PNP transistor. And now they apply to JFET. However, that will be also more complicated. Okay, so now first thing, we go back to working with gate or fixed device bias first. Now, you're looking into the circuitry here, okay? You can say, you can get the VGG equal minus 2 volt and RGG equal 220K. What they want to know? For the circuit show, they want to know VGS. You understand what that means for VGSQ?
The operating point.
Q point. Okay? That means at any point, I go in back to that one to show you. Any point in here, they get a Q point. If they draw the load line, okay? So when they get the, let's say, VGSQ, that means VGS at the certain point. IDQ, the same thing. VDS, VS, VD. Okay? Now, given to you, IDSS 5 milliamp, VGS off minus 4 volt. So the first thing they want VGS. Okay, now you can telling me VGS equal VG minus VS. That's basic definition. What VG equal? Is it 2 volt, right? That means VG equal VGG. What VS?
0.
So that's why I get VGS equal minus 2 volt. If you not follow it, let me know. The thing is this one you have to do all the time. Okay? And then they want to calculate the IDQ. ID will be calculated by this formula in here. Okay? They will be equal to IDSS mean 5 milliamp. ID 5 milliamp. 1 minus VGS. VGS equal minus 2. Divide VGS of minus 4. Square. Okay? And if you're doing a calculation right, you can get this to the answer right here. You get that? Okay. What VS equal? Right? S connect directly to the route. And now if you want to calculate the VD, that means the voltage here. And VD minus ID times RD. You already get RD 2.2K. VDD will be 12 volt. Okay? So that's why if you're doing a right one, you can get ID VD equal 9.25 volt. And if you want VDS, then VDS will be equal VD minus VS. And VS will be equal 0. Okay, so VDS equal VD. So you get any question on this calculation?
I have one for VG, and this is a bit back farther.
Okay.
How? No, it's in this question. How is VG negative 2? I don't. It's probably a dumb question,
You're
but I'm
talking
having
about
trouble
that
with
one,
it.
right?
Yeah.
Okay, what a question. How come they be negative?
So my question, I guess, is when we say VGG, and it over here it says VG, I'm assuming it's saying voltage at G, this point above the resistor, or are we saying it's VGG is just VG?
VGG is not VG.
That's what I figured.
It's a different power supply.
Yes.
Okay. Okay, they gave a
But isn't it true, Mr. Pham, that if the gate source is reverse biased and there's no current, then VGG is equal to the gate voltage?
you mean VGG equal VG, right?
Because there's no current flowing, because the gate source
No current
junction
flow here.
is reverse biased. There's no current. So in this case, VGG is equal to VG.
Okay, but the thing is they telling you the resistor is big. So that's why no current can be flowing. Okay, and you can explain another way. That means this will be a reverse bias. So that's why the current not flowing and VG and VGG will be the same.
Mr. Pham, I think I had the same question.
Okay.
I see the source as VGG, and then you say VG is equal to -2. So are you saying the resistor is so big that VG, go ahead.
Yeah, that resistor is supposed to be big. So no current flowing.
So then VGG, so VGG is the same as -2?
Now VGG is -2. They give it.
I mean, VG is -2 as well.
Right.
Okay, thank you.
Mr. Pham,
Yeah.
on the
Right?
at the bottom of that page, it say no, always ID is equal to IS, right? Can you explain that? I mean, voltage S is 0, right?
You say what
ID equal to IS.
ID.
At the very at the bottom, yeah, it say always.
That's like the formula.
Uh-huh.
Current ID here, right?
Yeah.
And the current IF here. All
Mhm.
the time. The same.
Even though VS is equal to 0?
That doesn't matter. When you're working with the JFET, then they're telling you all the time, ID, IS will be the same.
That's almost similar to the bipolar where IE and IC is almost the same.
IE and ID, no. That's
No, I didn't say B. IE and
IE and
IC.
IC. They differ in the bipolar. However, JFET, they give it to you for sure. You want to calculation, then ID must be IS, the same thing.
That's because, Joseph, in a JFET with a properly reverse biased gate source junction, there is no base current. So the drain current is exactly equal to the source current. It's like a valve. The gate acts like a valve.
I got you. Hey, thanks a lot.
Yeah, very good.
So if VGG was positive, the gate wouldn't open.
Okay, so you get through that. I want you to do. Okay, so on this circuitry here, they given to you IDSS. And VGS off. Minus 4 volt. Okay, so the first thing they want to know VGS Q. So you tell me what VGS Q equals.
Minus 1 volt.
They will be VG minus VF. And VG equal minus 1,
Minus 1.
minus 0,
Mm,
minus 1 volt. And number 2, they will be calculate the ID Q point. If you want to calculate the ID, the formula will be ID SF times 1 minus VGF, VGF off. Square, okay? So you're doing calculation. And number 3, they can be calculate the VD. VD will be equal VDD minus ID times RD. And if they want to calculate the VDS and VD minus VF, okay? And we already know VF equals 0.
What's that equal 0?
VF,
VF is in Frank? Oh,
okay, right here. So that will be go to guarantee you know how to calculate for the fixed bias. And that means you have to do it right away, okay? Only thing that when you have to substitute for the equation, take a little time. Other one. Then if you know how they're working, then you can get the answer.
Mr. Pham,
Yeah,
on number 4, okay, VDS is equal to VD minus VS, right? That's
Right.
an S. Okay, all right. It looked like a G.
okay.
Question, Mr. Pham, question.
Go ahead.
The general rule for the JFET, correct me, if the arrow is going into the gate, you have to have positive voltage for the gate to open.
You
And
mean
if the,
for the
if the-
get here?
for the gate to open with the arrow pointing into the JFET, that means the gate has to have positive voltage in order for this JFET to work, or considered to be on or off.
Okay, now.
No, I think that's a basic misunderstanding. the bipolar transistor requires a forward biased base emitter junction to work. The FET requires a reverse biased gate source junction to work. That's a basic difference. Right, Mr. Pham?
Right. That's not a like a bipolar.
So this
In a properly working bipolar transistor amplifier, you have a forward bias base emitter junction where there's base current. In a properly biased JFET, you have a reverse bias gate source junction. So there is no gate current, or essentially no gate current.
So with that JFET with the arrow going in, if we were to if
Telling you N channel.
right, I'm just trying to clarify the
And the gate have to be negative if you're using the fixed bias.
so for that gate it has to be a negative in.
Right. If you're reading through the handout for P channel, then the gate have to be positive voltage.
If the arrow was opposite, it would have to be positive, correct?
Right.
Thank you.
By the way, I believe in this program here, special for this semester, I get a one man, Richard Trill. He is really, really good. I appreciate whatever, try to make it clear for you guys. He get a master degree on AA. That means higher than what I get. I get only AA. And he also be director for a few company in San Diego. I really thank you for Mr. Richard try to make some more clear. That's what he talked to me. Make it clear for the student. That's very good.
Thank you, Mr. Pham. I appreciate that. I'm just trying to help.
Now, the thing is, we try to learn together. Okay.
Yes.
And I'm looking into your background, your history. Okay, perfect. Okay. And you said I still older than you do. Okay. And I still working, keep my brand, keep running. That's it. Otherwise, what can we do?
Both
I'm
of
not
them,
sure. Are you older than me? I'm 72 years old.
Okay. So
both of you guys are young men.
now we older than you.
That's what I said, Mr. Pham, you're younger.
No, I'm old. Okay. Anyway, we'll quickly go to this one. Then you can take the test. Now, this is another way. Sell buyer. The thing I want your guys to do, after we go through this sell buyer, you need the time to go over by yourself. Okay? Before we start in the next one. Sell bias, that means you don't have any power right here. Okay? On the fixed bias, you get a minus, okay, VGG, but no power. So that's why they call it. The effect will be on divide. Without the gate voltage here, they still working. Okay? Now, for the JFET, for cell buyer, they must be given to you this graphic here. Okay? Without it given to you, very, very hard to calculate it. Okay? And let's see, how can we do? First thing, this is the line they given out to you with the IDSS value and the VGS off. And now you want to find any point on the curve in order you can get the ID and also you can get the VGS. Okay, so they telling you the way we can do. Okay, now what VGS equal? VG minus VF. Okay, and VF, now you can see this is a VF right here. This is a VD. So the current flowing here supposed to be ID. IS or ID, same thing. Okay, so VS equal ID or IS times RS. Same thing when we can say they can be ID times RS. Okay, so now I going back here.
So that's Ohm's law.
Okay, let's see. VGS equal VG minus VF. Okay, equal VG minus ID times RS. So that is the VGF. Okay, then we try to see what VG equal. VG equal 0. Okay, so they can be 0 minus ID times RF. Okay, finally, VGF equal minus ID times RF. Then, if you want to calculate the ID equal ID SS times 1 minus VGF divide VGS off square. Okay, then you have to substitute the VGS here into the equation. Then ID equal ID SF. Okay, minus VGS. Now you can get a minus ID times RF divide VGS off. And square. Okay, so that's a very, very hard to do in calculation. You get one side here, you get the ID, and you get another side here, you can get the ID here. Okay, so they don't want to do this calculation. Normally, if you open any textbook for the technician, they not do it. Okay, they're not doing this way. They will be given to you the graph in here. Okay? This graph in here. And they
Mr.
want
Pham, raise it up just a little
the
bit.
graph to solving.
Raise your screen up just a little bit.
Okay?
Yes.
Now, how can we doing for this one? Okay? First thing, you need to draw the line. Okay? Wherever they cut the curve, that given you ID here, given to you VGS here, in order to draw the line. Okay? Now, let's see. VGS equal, okay, minus ID times RF, okay?
Please move on the screen.
Is it okay?
Yes, we can see the whole screen now, the whole slide.
Now, VGS finally equal minus ID times RF. Instead, you take that VGS, substitute into the equation, you're solving the equation. We don't want. And now, they given to you the graphic here. Okay, what you need to do is try to draw the line wherever they cut it. Okay, at the curve, you get the Q point. So first thing, VGS equal minus ID times RS, and you can set ID equal 0. Then what VGS equal? ID equal 0. So VGS equal 0 times RS equal 0. So that's why they gave it to you the first point right here. Okay? And now you need the second point. A second point, you can give a value, ID, equal any number here. Okay? Any. But they must be less than 10. Must be less than IDSS. So if I say I can take they equal 10. Okay? That means ID equal 10. Let's see. Now we can pick any point here. 1, 2, 3, up to 10. Okay? If I said I can pick equal 3.
Mr. Pham, if you pick 10, then ID would equal IDSS, so you don't want to pick 10, right?
This is basically from the textbook, they pick 10. Okay? But I said you can pick the second point with the ID equal any, not 0, and basically up to 10 maximum. So if you pick it up equal 3. Okay? So now if ID equal 3, right? So what we need to do is we need to get the VGS. Okay? So minus 3 times RS will be 0.7470. So that's why you can get the VGS. So you can get the second point, okay, will be a VGS. So if you get the 3 in here, so 3 times 0.47, see what you get. 3 times 0.47. So you get 1.41 minus 1.41. Okay? This is a -1, -2, okay? -0.41, okay? So that look like here, minus right here, okay? So you get a 3 in here, you draw the line, okay? And you get a -1.4 right here. You draw another line, okay? So they cut the second point right here, and you draw the line. They cut anywhere here. That will be given you ID here. And you're going down, VGS here. Okay, anyway, for the sale buyer, normally they given a graph to solving the problem, not really go detailed calculation. In order to, when you get a wrap, in order to do it, you have to get 2 points. 1 point you can say A, another point you can say B. Point A here, you can get ID 0, so you get VGS 0. This is a point. And the second point, you can give any ID value, okay, from 0 up until 10. Then you calculate the VGS, okay? And after you get a VGS, that's why you can draw ID here, VGS here, and they hit it right here, okay? You draw the line, okay? So they can cut it. So,
Mr. Pham, I'm not sure it's clear how you got point B. It says set ID equals any value between IDSS and 0, but you've got point B equal to IDSS.
okay, now.
So I don't understand.
Okay, the first one, you pick a 1 point, right? I pick a right here. That means I pick ID equal 0. This is the first point. ID equal 0. And from this equation here, then you know VGS equal 0. That's why you get the first point right here. In order to draw the line, you need a second point. What I'm saying is you can pick any value of ID. You want here, you want here, you want here, you want here. Okay? In this example, they pick at 10. ID equal 10. So what VGS equal? -10, right? Time. RS will be 0.47. Okay? So what you get? They will be -4.7. Is it right?
Yes.
Okay.
So -4.7, -1, 2, 3, 4. This is a 4.7 right here. Okay, so the first thing.
Okay. Yeah, that's a better explanation. I like that. Yeah.
Okay.
I like that.
The first thing you select equal 10, you draw the line 10 right here, right? The second thing you get for -4.7, you draw here. That's the second one. And they hit point in here, okay? So basically you draw the line from point B to point A, and they cut the curve at this point. That's what we call a Q point. And from this one, you want current ID, they can be 1, 2, 3, 4, 5 milliamp. And if you want VGS, then you can get -1, -2, maybe -2.3 or 4. That's okay.
Right.
Okay.
And this is the quiescent point or the operating point for the transistor around which the AC signals operate.
Right. So that's a graphic, but the thing is, we also not using, okay? They normally, what happen is, when they want to give it to you, okay, on the fixed buyer, okay, then normally they give it to you some different value, okay? That means if they given on this one here, they have to be given you the graphic, okay? Otherwise, you have to do your calculation. That not happen. So normally, in this case, they will be given to you, okay, I given to you ID, 5 million, and you're doing the red calculation. You see that? You don't need the graphic, and you don't have to substitute into the equation to solve it. That's one way. The other way, if they not giving you this right, they given you here. They said they given you Vs equal 1 volt. So when you get a Vs equal 1 volt, automatically you know the current ID here, or Is, same thing. You take 1 volt divide your Is. So that's why normally that happens. Okay, and normally that's what you deal with. If they using the cell bias or voltage divider bias, they need the graphic. If they not given the graphic, they will be given to you either voltage VD or ID or voltage VS for you to doing calculation. Okay, so now we need the time to take the test.
Question real quick, Mr. Fan. Question?
Yeah.
Looking at the drawing, we see the blue line, and I can tell that from 10 down to Q, it's almost a straight line. But from Q to -8, what determines that slope? What determines the angle of that slope for the blue line?
You mean the current here?
Yeah, that blue line that goes from Q down to -8. What is determining how that slope has that angle?
I think I can help here. If you go back to the equation for drain current, it's a quadratic equation. So it's ID equals IDSS times 1 minus VGS over VGS off squared. So basically what you're looking at in that graph for VGS, IDS versus VGS is a square law device based on that equation.
That's what puts a curvature in it versus a straight line from 10 to -8.
Yes, it's a square law device. If you maybe if Mr. Pham can go back to the basic equation for ID, you'll see that it's a ratio squared. So that's why it's not a straight line. It's a quadratic equation.
Hey, Richard, what I was going to say is it looks almost like he's talking about the curve part. It looks almost like when you're drawing a parabola, but then you cut it in half. Where it starts, starts to curve at the bottom.
A parabola is a form of a quadratic equation. So that's why it's curved and not straight.
Okay, so basically you don't have to pay much attention on about this curve.
Pham, I have another question, another basic question.
Go ahead.
The name of the green or blue curve is still the transfer conductance curve?
That's the equation for the ID.
So here, what is the name of the blue curve?
That's what they call a transfer function. And basically, this
It's,
equation for the ID equal what? IDSS time 1 minus VGS over VGS of square.
Okay, transfer function.
but it's transconductance because it's output current over input voltage, right?
Right.
Okay, got it. Thank you.
Okay, now let's see. We need to take the test. Okay, I need to stop that guy.
I'm going to sit this one out.
Is this something that we're turning in?
Well, after you're done, you have to upload it.
E-quiz, I see it now. I was looking before, I didn't see it. There it is.
Upload between now and 8 in the morning.
Okay, where is it? Is it a handout?
No, upload this between the end of the test until 8 in the morning.
This, he just put it up so you can download it off the front page.
Oh, great, thank you.
Sure, sure.
And now,
number 5, I think D should be answer A and B.
No.
And C, you get it. It's basically the quiz for technician. That only requirement you can do it right away. Not don't need to open any textbook or any note, anything. You get to interview, you don't have any more chance.
Hey, Mr. Pham,
Yeah.
before I found the answer document that you downloaded, you had already passed through the first 3. So could you back up for a little bit, just for anyone like me who didn't find the answer sheet?
Okay, so you can see it tonight.
Yeah, you can watch the video and then you can do the testing there.
Okay, that's cool.
Right now,
Okay.
running. We cannot stop it.
Any way to decrease the screen, please?
No, I cannot. Let's see. No.
Yeah, for 16, we can only see A and B.
A and B is all you need.
Oh, okay.
Same for 17. A and B is all you need.
So you have 50-50 chance of getting number 16 and 17 correct.
Oh, can we go back to that page?
I can try to see. Let's see, I have to stop that guy.
Okay.
Okay, now. Okay, let's see. That number 17 on the A and B. Okay,
Q25.
and number 1, 2, 3. Okay, any more numbers you want to see?
Can you go back to the last slide, please?
The last one,
15, 16,
17, 16, 17.
Thank you.
Thank you.
okay, we'll see you guys next week.
All right.
Thank you. Night.
Good night.
Thank you.
Good night.
Good night.